Hi, welcome to this video on the introduction to equilibrium. So as we're beginning our unit on equilibrium, we're going to talk about equilibrium as a general overall, just the different parts of the equilibrium and understanding. And then we'll spend time in the units as we go up ahead talking about specific types of reactions and how their equilibrium is different. So in general equilibrium in this section, this is just a background information on some equilibrium and kind of looking at what is equilibrium. So first off, let's start with what is equilibrium. So equilibrium, when we talk about it, is equal, right? That's typically what we think of. It's actually the state in a reaction where the rate of your forward reaction is equal to the rate of your reverse reaction. So at that point, we're not seeing an overall rate change happening anymore. So it's basically when we get past, in kinetics, when we're talking about the rate of the reaction, it's when we get to that point where our reaction rate has leveled off. So concentrations at this point of all the reactants and the products are going to remain constant with time. So once equilibrium is established, we know that that is not going to be changing overall. It doesn't mean that we aren't making product, but it means that if we make product, we're going to reverse back and make reactant. And then we'll make product, and then we'll reverse back and make reactant. So it's an even exchange of reactants and products occurring. So in stoichiometry, what we've basically talked about up until now is that all of our chemical reactions go to completion, meaning if I have 50 grams of a reactant, we're going to have 0 grams of reactant at the end. That's not really the case with reactions. Really, we have some reactions that are going to go more towards completion, but most of the time, our reactions don't go all the way to completion. So if I have 50 grams, really, I may not actually make 50 grams. A lot of times we use all 50 grams. Now, a lot of times we assume the reactions go to completion. So many chemical and physical processes are reversible. So example, evaporation and condensation, right? So evaporation going from the liquid to the gaseous phase, and then condensation going back, gas to the liquid phase, right? Or dissolution to precipitation. So dissolution is dissolving, so a salt dissolving, but then letting it go back to a precipitation or a solid. Redox reactions, the gain and the loss of electrons, right? Those are reversible. We indicate a reversible reaction or something that doesn't go all the way to completion with the double arrow. So when we use that double arrow, we're usually referring to some sort of equation or reaction that is at equilibrium. Dynamic equilibrium is a term we use that indicates, again, when we see those double arrows, that the reaction is proceeding in both the forward and the reverse direction simultaneously. So in this factor, when we see those double arrows or dynamic equilibrium, what we're basically saying or would see is there's no observable changes that are occurring because the rate of each direction in the reaction is equal. So we would not see a difference. Like it would look like we stopped making product, but really, we're really making equal amount of product and equal amount of reactant at the same time. It's going back and forth. So if the rate of the forward reaction is greater, that's supposed to say is greater than the reverse, then we would consider our products to be more favorable, or we would see more products being formed. If the rate of the reverse reaction is greater than the forward, then obviously we would have less products being formed. So the greater the rate of the forward reaction typically tells us that we would be more product favored versus reactant favored. And we'll talk about those terms a little bit more. At this point, when we're at dynamic equilibrium, the concentration of your reactants and products is constant. Keep in mind, really important, I'm going to circle it, that doesn't mean that the concentrations are equal. So I can have 1 molar of a reactant and have 0.1 molar of a product. And so they're not equal, but they are going to remain 1 molar and 0.1 molar is really what we're saying. So in our graph, over here was my kinetic stuff, right? So this is what we were studying with kinetics. So concentration versus time, and we were doing our integrated rate law. When we get to this section, or this chapter, we're focusing on this portion where everything levels out. This is the equilibrium portion. This is where we see the concentrations of my reactants and my products not changing drastically anymore. They've leveled off, and that's how we know equilibrium has been established. So there's different ways that we report what the equilibrium is. We can calculate what equilibrium concentrations are and things like that. This is using the equilibrium expression. Now it's gonna seem kind of similar to the kinetics rate law and rate expression, but it's very different. So we need to keep those very clear and separate. The equilibrium expression is basically shows how we would calculate the equilibrium concentrations of each of our reactants or products. So it is temperature dependent, so that is important to remember, okay? So equilibrium is temperature dependent, just like our K constant in kinetics was temperature dependent. However, if we change concentration or pressure, that does not change the equilibrium, okay? The temperature doesn't change with concentration or pressure. I almost said that wrong. So equilibrium is temperature dependent. However, it does not change with concentration or pressure. All right. So I can change my equilibrium if I change my temperature, but it's not going to change my equilibrium just because I have more, like a higher concentration or a higher pressure of gas. All right. So let's talk about the equilibrium constant expression. So this is how we would write the constant, and we would use this equation later. I'll show you how. The equilibrium constant is used, we use that letter K. Okay, so Kc means K for concentration, Kp means K for pressure, if we're doing gases, things like that. It's all based on our chemical reaction. Now here's one thing that is very different, okay? In a kinetics equation, we only looked at reactants. In an equilibrium expression, we are actually looking at products compared to reactants. So we include both, okay? So in our equilibrium expression, when we write it, okay, it will always be, the numerator will always be your products, and your denominator will always be your reactants. So your K, whatever K it is, it doesn't matter. Sometimes we write KEQ, right, is always going to be concentrations, or it could be pressures of your products over concentrations or pressures of the reactants. So we take into account both. And because they should be leveled out, your K should not change ever. So if I increase my amount of product, then I should see an increase in the amount of reactants, right? So these should be changing together. They should be constant rates. So therefore, when our constant concentrations and constant rates at those points, so my equilibrium should always remain the same. So the equilibrium constant, we use the capital K instead of a lowercase k. So be careful on that. So we can write it different ways. EQ is just general, kind of like when we are doing enthalpy and we just say enthalpy of the reaction. We're not being specific on what kind of reaction. So with KEQ, it's any kind of equilibrium. Kc is specific to concentrations, which would be used for solutions with molarities, right? We would have to have molarities. Notice we use the brackets, right? So in this scenario, your C, it's your bracket, so concentration of C. And notice the other thing that's really important is the coefficient is used from the equation. We did not do that in kinetics, okay? So we use the coefficient in our chemical equation for our power of whatever that reactant or product is. Kp is the same scenario. In Kp, we've got our products, but we're using a capital P, right? So Pc, it's kind of like when we did gases, and I would say the pressure of helium, whatever. So it's notice we do not use brackets no brackets. This is really weird and kind of, I know, seems dumb, but in AP or really in chemistry, we don't use brackets unless we mean concentrations or molarities. So in the AP exam, they really hate it if you use brackets when you're talking about pressures. So do not use them. Sometimes they will not give you the point for it because it's technically incorrect if you use the brackets. You're assuming concentrations, not pressures. So that's why you see parentheses instead of the brackets. So I have a little description over here. So if in any way you forget what these mean, right? The brackets are for concentration. P indicates pressure. Kc is for concentration, which is aqueous solutions. Kp is for partial pressure of gases. And then the K values are a lot of times written without units. We don't really care about the units because your units on the top and bottom are going to cancel out because they're molarities over molarities or ATMs over ATMs or whatever. So we typically write our equilibriums without any units, which again is different than the K constant that was a lowercase k from kinetics. All right, so an example. The reaction between steam and carbon monoxide produces hydrogen, carbon dioxide gas in a closed vessel at a high temperature. So we have to first write the reaction. So we would have the reaction between steam, which is water, gas, hopefully you know that, and CO, right, is going to produce hydrogen, which is H2, right, and CO2. So then we look at this reaction. We have to make sure it's balanced, which, oh, nicely, it's already balanced. Okay, so everything's 1. If I didn't balance that right, I'm sorry, but I'm pretty sure that's right. Okay, so then from here, we can write an equilibrium expression. Now, these are all gases. It kind of depends on what we were given, but it's very unlikely that I'm going to be given the equilibrium, like concentrations for gases. So typically, when we write it, it would be a Kp, right? That's going to equal, and I'm going to use the parentheses instead of brackets, right? Products, I'm going to have H2. Oh, I missed my pressure. Hold on, let me erase that. Let me try that again. So pressure of H2, right, to the first, which you don't really have to write the ones because that's the coefficient. The pressure of CO2 to the first over my reactants, which in that case is going to be pressure of the water or steam specifically, so water vapor, and pressure of CO to the first. All right, so that would be my equilibrium expression for that chemical equation. Pretty easy. It just goes with what you have and you're using the coefficients. One thing that's really important to know, and we'll hit this several times as we go through, is pure solids are not going to appear in your expression. Okay, so pure solids are not going to include, because they're not going to change concentrations appreciably. Pure liquids, the same scenario. We do not appear in the equilibrium expression. So water, for example, is a pure liquid, water liquid. Now water gas up here, that was okay because it was a gas. It was the water vapor. But if water liquid, water solid, we would not include. So we would leave those out of our equilibrium expressions. And one of the things like with water, it's a pure liquid, 55.5 molar is not going to change. I mean, that's essentially when you're using water as an aqueous system, your water liquid, even if you are producing water liquid, it's not going to drastically affect the concentration because you already have a huge concentration of water in the aqueous solution. So typically, if it's a combustion reaction or something like that where you're producing water vapor instead. So then that would be included. Okay, so the equilibrium position, understanding what K means, okay? So whether the reaction lies far to the right means it favors products, or to the left favoring reactants depends on 3 things. So there's 3 important things that determine, is this going to make more product before it levels out? Is it going to make more reactant before it levels out, or what? And those 3 things are really easy. One is your initial concentrations, okay? So this hits back to kinetics. The more collisions, the faster the reaction happens, right? And higher concentrations are going to tend to reach equilibrium a little faster. relative energies of reactants and products, right? Nature goes to minimum energy, so the whole energy of your reactants and products is important. In nature, you know, your stuff is all trying to achieve every compound element, whatever it is, a lower energy state, right? And then the degree of organization of your reactants and products. For example, gases versus solids, that kind of scenario. So nature prefers a maximum disorder, meaning we're going to prefer things to be in the gaseous phase to have a greater equilibrium position or to change the equilibrium position. That's typically why we use aqueous solutions and gases and we ignore solids and liquids, okay? So the significance of the K value. All right, K constant tells us a whole lot. Remember that K is really your concentration or your amount of product, right, over your amount of reactants. So then we have to think about what does that mean? And we'll hit this a little harder later, so I'm just going to briefly introduce it. But if K is greater than 1, right, that means I have higher amount of product compared to the reactants. Does that make sense? That's why that would be product favored. Because the only way to make this value to be larger, it means that when my reaction reaches equilibrium, I have a higher concentration of product than I do reactant. So my reaction preferred to make product is what we're trying to say there, okay? So when we see a K value that's greater than 1, it usually means that it's product favored or it prefers to make product in that reaction. In something is a K that is less than 1, right, then that means I have more reactant than I do product. So that's something that doesn't prefer to make product. It wants to stay in the reactant phase. A little bit of it will go to product, but not as much. So for example, this would be something like when we're talking solubility, when we talked about our weak acids versus our strong acids, right? Strong acids, we say 100% dissociate into products. They're very product favored and have really high K values. There's very little reactant left. But a weak acid doesn't prefer that product favored. It does go that way a little bit and make a little bit of product, but it prefers to stay in the reactant. So we have a higher concentration of reactant than we do product. So that's essentially the only difference. So that's what we're looking for. All right, so in exercise 1, I already did an example for you, but we'll do another one, all right? It says, write the equilibrium expression for the following reaction. So my equilibrium expression is K equals, and we're going to do our products, right? And all of these are gases or aqueous, so none of these are aqueous though, so it won't matter. So these are gases, so I'm going to do a pressure. So I'm going to do Kp instead of Kc. So we're going to do pressure of NO2, and we're going to raise it to the coefficient of 4. And we're going to do pressure of water vapor, and we're going to raise it to 6 over my reactants, which are going to be the pressure of NH3 raised to the 4th, and the pressure of O2 raised to the 7th. That's essentially all it is to write your equilibrium expression. So they're a little easier because they are taking into account everything that is either aqueous or a gas and how they affect or what they are in concentration-wise or pressure-wise when you reach that equilibrium spot. All right, let's see. Let's move up. All right, so I am not going to do these next ones with you. I want you to try exercise 2 on your own. So do those and submit those, okay? So in order to do these, right, you're going to have to write correct chemical formulas first, and then you would go into doing your, correct chemical formulas, and then you would write your equilibrium expression from that. Keep in mind, when we look at this, solids wouldn't be included. Liquids wouldn't be included, okay, when you write your equilibrium expression. So pay very close attention to that. Now, if it is aqueous, then yes, it would. Okay? All right. I will check those for you just check your notes. All right, looking at changing the stoichiometric coefficients. So when the stoichiometry of your equation changes, right, your factor of K is going to change as well. So you have to know these rules. They kind of make sense. They're a little different than what we would do in like redox reactions or in enthalpy reactions when we're doing Hess's law, because they aren't exactly the same thing. But you want to make sure you're paying attention to that. So for example, if I multiply K, right? So if I multiply by a factor, like I take K times 2, then I'm going to see it be raised to the power of that factor. So for example, if I multiply my coefficients by 2, or I double my reaction, then I'm going to see K be squared, right? Or if I triple my reaction coefficients, then K is cubed, etc. If I reverse my equation, instead of making it a negative, we do an inverse of K. Okay. Adding the equations means I multiply the K values. So if I add and multiply together. These are things you need to know. Okay. They're super easy questions, but they are things that you need to recognize are going to happen. So for example, in exercise 3, it gives me 3 equations, right, or 3 concentrations. So the following equilibrium concentrations were observed for the Haber process. So first thing it wants me to do is calculate the value of K at 127 for the reaction as is. All right, so I have my K. It's giving me concentrations. So this is Kc. And the Haber process is actually the process of making NH3. So it's N2 plus 3 H2s, making 2 NH3s. All right, so when we look at this, we've got this set up. So we're going to write our products, which is going to be NH3 squared. So it's concentration, so notice I'm using brackets. And I'm going to do H2s cubed. You could do the N2 first. I just kind of flipped it, sorry. N2, oops, to the first, sorry. So don't be messed up by that. You can do whichever order you want. I just looked at the H2 first and threw that on there. Okay, so to calculate your K value, right, so my Kc normally would be plugging that information in. So I'm going to plug in the stuff. I'll change my colors. I'm going to plug it in exactly like it is. So I'm going to take my NH3, so that's going to be 3.1 times 10 to the negative second molarity squared over, right? And then I'm going to do my H2 because that's how I put it in. So set it up, pretend my 3 looks better, 0.1 times 10 to the negative third molarity cubed times my 8.5 for my N2 times 10 to the negative 1 molarity, and that's going to be to the first. So I'm going to calculate that out. All right, so I want 2 sig figs because all of my concentrations had 2 sig figs. So it's going to be 3.8 times 10 to the 4th. All right, and I don't really care about units here. Okay, yeah, I know technically units look like they're not going to cancel, whatever, but we're really not as concerned about the units because everything's in the same unit and stuff like that. So we don't write our units. It's not a big deal with our case. All right, so the question in B asked me to, oh man, I did it right. Okay, calculate the value of the equilibrium constant for this reaction. So notice what happened in this reaction. First, we reversed the reaction, right? And that's essentially it. So it was reverse the reaction. So if I reverse the reaction, then I am going to do the inverse of K. So my new Kc value here, right, in this equation is going to be 3.8 times 10 to the 4th inverse to the negative 1, or you can just do 1 over on your calculator, right? So 1 over whatever that was that you just calculated. And so when I do that, I get 2.6 times 10 to the negative 5th is the new K value. So that would be the K value for this equation, right? What about in C? So I calculated the value of the equilibrium for this reaction. Oh, somehow it missed that. Supposed to be an arrow. Okay, so what did we do here? Well, we took our coefficients and we divided it by 2, or if we want, we multiplied it by 1/2, right? Essentially same thing if we look at it, right? So if we multiply it, that would be what we would do to the K value, right? But it would be its power of. So we would basically take Kc, which was 3.8 times 10 to the 4th, right? And we're going to take it to the power of 1/2, which is essentially like square rooting it. Hopefully you guys realize that and remember that from math. So you're going to, but you can easily go put it in your calculator and just raise it to the 1/2, right? And that would essentially be the same thing, but it's square rooting. So when I find my answer to this with 2 sig figs, it's going to be 1.9 times 10 to the 2nd for that K value. So this equation has a K value that is equivalent to this, okay? So it's just taking it to a factor of based on whatever our reactants and products are. It's adjusting that factor. All right, so in exercise 4, show that the equilibrium constant is the same in both of these cases. So it's giving me 2 experiments. I'm going to do experiment 1, and I'm going to have you do experiment 2. So it's the same reaction. So the following results were collected for 2 experiments, right, involving a reaction at 600 Celsius between gaseous sulfur dioxide and oxygen to form gaseous sulfur trioxide. So first thing is sulfur dioxide, SO2, right, plus O2 to form SO3. All right, so balancing that, I would double my SO3s because I need that to be an even number. That gets me to 6 oxygens and 2 sulfurs. Then I'm going to double my SO2, and that's going to give me 2 sulfurs, and 4 plus 2 is 6 oxygens. Okay, so there's my reaction, all right? My equilibrium, or Kc, is going to be products, so SO3 concentration squared over my products, which are reactants, SO2 squared over O2 to the 1st. All right, so that's my Kc. So then show that the equilibrium constant is the same. So to plug in or find the equilibrium constant, I'm going to plug in what I have. So I'm going to use the equilibrium amounts. I don't care about the initials, okay? So that is important, I think. Yes. All right. So I'm going to plug in. So I got Kc for this is experiment 1, okay? So I'm going to plug in what I have. So experiment 1, Kc, I'm going to start with 3.50 molar squared, right, over 1.50 molar squared times 1.25 molar. Notice also I didn't point this out earlier, but when you write your equilibrium expression, you have to use brackets for concentrations. I can use parentheses once I put molarity because we know it's concentration. So it doesn't matter once you input the molarity into your problem. All right, so on this one, my K value is I'm going to go with 3 sig figs, so 4.32 for my Kc value when I plug that in. All right, so if we do experiment 2, right, if it's the same equation at the same temperature, we shouldn't see the equilibrium change much. Now, it may change, we may see a slight difference because it's experimental data, but it should be about 4.3, okay? So same thing, we plug in Kc here. Notice I'm ignoring initial concentrations. I care about my equilibrium concentrations when I'm plugging in, okay? So Kc would be 0.260 molar squared over 0.59 molar squared times 0.0450 molar. All right, so when we plug that in our calculator, I suggest you practice plugging these in your calculator just to make sure you don't make mistakes too. I know you can wait for me to do it, but practice, it would help. So on this one, actually on this other one, I put the wrong answer. This one was 4.36. This one is 4.32. So we're not seeing an appreciable change here. Like it's pretty much the same K value. So let me erase that. Put that the way it's supposed to be. 3, 6. Okay. So it went change just a little, but not enough to make a difference. So because it's the same reaction at the same conditions, okay, of temperature, the K constant is exactly what we say it is, right? K constant is the same. That's the key here. All right. Okay, in this part, it's talking about Kc versus Kp. So a lot of students get confused on this, and this is the last little thing we need to talk about, is that Kp and Kc are not interchangeable. So if you have a Kc value, you can't assume it's the same value for Kp. There is an equation you can use to convert one with the other. So if you have a value of Kc, let's say, you can find Kp, okay, but you have to calculate it. This is one that you would have to memorize if you wanted to use this on the AP exam. It's not on your formula chart. There's other ways to go about finding it, and I will show you later. It's a little bit more work, but it's easier just to know the politically correct is what we call it, the PC equation. So the delta N is your change in moles, right, of gas that is going from reactants to products. So remember, delta N is going to be like your final, your moles of product minus your moles of gas is reacting. It's only moles of gas, okay? R is the universal gas constant that we would use for our gases, and your temperature has to be in Kelvin because your R constant is in Kelvin. One thing to remember is Kc is equal to Kp if the moles of product and moles of gaseous reactant are equal. They use that a lot as a question because they want to throw you off. That's the only time it is equal. But a lot of times they'll throw that in on a multiple choice question where you have 3 moles of reactant gas and 3 moles of product gas. So really the Kc it's giving you is the Kp value because they're the same thing. But if it's not, then you actually have to calculate it. All right, so let's look at this example they've got for exercise 5. So in this example, the reaction for nitrosyl chloride was studied at 25 degrees Celsius. Pressures at equilibrium were found. Notice at equilibrium. So we could plug those into our equilibrium expression. All right, so we're going to set up our equilibrium expression first. So K, in this case, pressure, so Kp equals, right? Let's see, Kp, we're going to plug in. It's going to be pressure of NOCl, and that's going to be squared over pressure of NO squared times pressure of Cl2 to the first. So then we're going to plug in the actual pressures we have, right? So when we plug in the actual pressures, we would take 1.2 atms squared. Notice I'm in my equilibrium expression, I didn't use the brackets, right? Because we're talking pressures, I use the P's instead. My pressure of NO is going to be 5.0 times 10 to the negative 2 atms squared times 3.0 times 10 to the negative 1 atms. All right, so when I plug that into my calculator, Kp equals, we're going to do 2 sig figs, so I get 1.9 times 10 to the third. Okay, so Kp is not going to be equal to Kc, right, unless it was equal moles. Well, when we look at the moles here, so it says using the value of Kp that we just got, we want to find the value of K, or Kc specifically, right? So first thing we check is this is 3 moles of gas, right, and we're making 2 moles of gas. They're not the same. So Kp is not equal to Kc. That would only be the case if those were equal moles. So darn. So now we have to use the politically correct equation. So it's really easy. It's politically correct for PC, right? So that way you remember which one goes where. So KP is equal to KC, and then you have to make sure you do R and T in parentheses raised to your change in moles. Okay? So our change in moles is going to be product, so delta N is product moles, so 2 moles of product, right, minus 3 moles of reactant. So make sure you do that because you do it the correct way because you want to have the right sign. So delta N is going to be -1. All right. So then we go to plug in. So we know our KP, we just found it, is 1.9 times 10 to the third equals KC, we do not know. RT, R is 0.0821 liters times ATMs over moles times Kelvin, right? And my temperature, oops, I did that wrong. So my temperature, I'm going to put this brackets around that, is going to be 25 degrees. So that's 298 Kelvin, right? We want to put it in Kelvin. And we're going to raise that to -1. So we're going to calculate the 0.0821 times 298 first, and then raise that to the -1, which is really inversing it, right? And so I get 1.9 times 10 to the third equals KC times, and I get 4.087, whatever, something, times 10 to the -2. All right, so if we were paying attention to this, this is moles. So moles cancels, Kelvin cancels, and then ATMs is the pressure, whatever unit. So it's liters times ATMs is really what we're going to get, value, whatever. I guess moles technically doesn't cancel, the ATMs cancel. Okay, but we don't really worry as much about canceling the units. It's a little more complicated than that. So then I'm going to take my 1.9 to the third, and I'm going to divide it by that value. And so my KC value, again, not worrying about units, is going to be 4.6 times 10 to the fourth. Okay, so notice KP not equal to KC because they are not equal moles. So that's very important to recognize. So in this video, we spent time practicing, one, understanding equilibrium in general. So equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. We spent a little time understanding how to write our equilibrium expressions, the difference between a KC expression and a KP expression, using our reactions, right? And then how to plug in to our equilibrium expression to find the equilibrium constant. And then we also talked briefly about when my equilibrium constant is greater than 1, for example, in this this one that we just found, that tells us it's very product favored. So that means that we tend to make more NaOCl, and so we're going to tend to proceed in the forward direction in that reaction. When we have a low K value, we're going to see that when it's a negative K value or like negative exponent or a low K value, we're going to see it be more reactant favored, okay? And then we practiced how to convert KP to KC after we find those constants, and then what to do if we manipulate the equation with the K values to find those as well. So not too hard. I know it's kind of a lot I just threw at you. We're going to practice it some more in class, and then we'll talk a little bit more about the change in K values and what those mean, okay?